Let's finish off this chapter by looking at the concept of density. So density is an example of a measurement which will contain units in both the numerator and denominator, like we just looked at in the last video. So the equation for density is it is mass per volume. So for example, water has a density of about 1 gram per milliliter. Note, you will also sometimes see it written 1 gram per cubic centimeter. But as we learned in our conversion factors, a milliliter and a cubic centimeter are the same thing. So just know we don't mean anything different when we say either of those. What this means is that if I have 10 milliliters of water, it's going to have a mass of 10 grams. If I have 1,000 milliliters of water, then I'm going to have 1,000 grams. What you'll notice is when I talk about that, the mass goes up as the volume goes up. But what is also true is that density doesn't change. I can have a swimming pool full of water, and it will be the same density as a small cup of water. The reason for this is density is something called an intensive property. So an intensive property is a property that does not depend on how much of the material is present. So our swimming pool has the same density as our glass of water. Not all properties are like this though. So extensive properties are ones that do depend on how much of the material is present. So our swimming pool has a much higher volume than a glass of water, unless your glass is incredibly big and made for a giant, or you have a swimming pool made for a small mouse, maybe. But in general, swimming pools that humans use are much higher in volume than glasses of water that humans use. So let's see how we're going to use this to help us solve a question. So I'm going to have a jet, and I'm going to fuel it with 1.425 times 10 to the 5th liters of fuel. I'm going to know the density of this fuel is 0.7680 grams per cubic centimeter. And I want to know what is the mass of that fuel in kilograms. So this problem is a density problem combined with some conversions as well. So let's see, what information do we know? We know the volume of the fuel. So this is volume. We know the density. So those are the two things we know. And what do we need to find? We need to find the mass in kilograms. So we know V, we know D, we need to get M. So if we want to set this problem up, we need to make sure our units match, because we know our equation was density, that should be in, equals mass over volume. The issue is, well, first let's rearrange it. We want to know mass. So I'm going to multiply both sides by volume, and I'll have volume times density equals mass. Now if we were to just do this though, you'll notice the units don't work out. If I multiply a liter times grams per cubic centimeter, nothing cancels out the liters or the cubic centimeters. So we need to get them in these same units first before we can do that. And then we also have some conversions to do. So let's start with this. So we know grams per cubic centimeter, we know liters. So I'm going to try to get my liters into a volume unit that matches this cubic centimeter right here. So my 1.425 times 10 to the 5th liters. I know that 1 liter is 1,000 milliliters. And I know that 1 milliliter is 1 cubic centimeter. So if we plug both those in, or all those numbers in, we have 1.425 times 10 to the 5th. We're going to multiply it times 1,000. So we're going to get 1.425 times 10 to the 8th cubic centimeters. I didn't give myself quite enough room. So now this matches the units of our density. So now if we plug it in the equation, the cubic centimeters will cancel. One of them is in the numerator, one of them is in the denominator. So let's plug this in. We have 1.425 times 10 to the 8th cubic centimeters. We're then going to multiply it times our density, which is 0.7680 grams per 1 cubic centimeter. So the cubic centimeters will cancel. We do that, 0.7680, and we're going to get 1.094 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. Oh, right, that makes sense. They should match. So 1.904 times 10 to the 8th grams. But it asks for it in kilograms. So 1.094 times 10 to the 8th grams. We know that there are 1,000 grams per 1 kilogram. So we do that, we divide by 1,000, the grams cancel, and we're going to get 1.094 times 10 to the 5th kilograms. Note that I kept the right number of significant figures throughout. The problem had 4 sig figs, so that's what I used as I solved my problem. Sorry for coughing in the mic. Just a second. I figured you didn't need to hear any more coughing. Now, this is one way to solve this problem. You'll notice it was kind of long. What I want to show you is there's actually a way I could have shortened my steps a little bit. So let's clear all this. And let me show you, I'm going to do the same problem, but I'm going to solve it in a slightly different way. What's going to be true, anytime you have an intensive property like this, I'm going to point out you can use it like a conversion factor. So every 0.7680 grams is equal to 1 cubic centimeter. So what that means is I can actually do this all in one line. So my 1.425 times 10 to the 5th liters, what we know is that 1 liter is 1,000 milliliters. We know that 1 milliliter is 1 cubic centimeter. We then know that 1 cubic centimeter is 0.7680 grams. We then know that 1,000 grams is 1 kilogram. And that way I can plug them all into a single line. Please note that if you don't like this thing, like what I just did looks incredibly foreign, feel free to use the density equation and do it in those smaller steps. Both give you the right answer. I just wanted to show this because sometimes times can be hard for people. So I plug all this in, I should get the same answer. I will make sure I do and that I did not somehow make the rules of math stop working. Or more likely make a mistake somewhere in my writing. So yes, I also still get 1.094 times 10 to the 1, 2, 3, 4, 5. Yep, 10 to the 5th. Kilograms of fuel. So you'll notice both ways got me the same answer, and it's okay to use either. Whichever you feel more comfortable with, feel free to do that. I just wanted to show this. When I solve some problems, I'm going to use, there are a couple others that are going to come up. Like in the next chapter, we'll have a term called molar mass, and we'll use it similarly, where we can go from one thing to another, but one in the numerator, one in the denominator. So now let's have a problem for you to try. So the proton has a radius of approximately 1.0 times 10 to the negative 13th centimeters and a mass of 1.7 times 10 to the negative 24th grams. I want you to determine the density of the proton under the assumption that it takes the shape of a sphere. And I provided the equation for the volume of a sphere in case you don't remember. Please note, this is something I know you don't have a lot of familiarity with, so if your number feels really big or really small, that's okay. Go with that. So give this a try, and I'll go over it afterwards. Let's write out what we know first. So this is our radius right here. This is our mass. Our equation for density is mass over volume. So since we want to determine the density, I need to know both the mass and the volume. We already have mass. That goes up there. We're done with mass. But volume, we're going to need to plug our radius into this equation. This is where I want to point out, sometimes you might have to use an equation you haven't used directly but will provide for you. So for this case, you don't have to memorize the volume of a sphere. Although if you happen to already know it from math, that's nice, but if you didn't, that's okay. You can just plug it into this equation. So our volume of our sphere, so this is the shape we assume our proton's going to take, is 4/3 times pi times our radius, which is 1.0 times 10 to the negative 13th centimeters. We're going to cube that. So let's see. So I'll do 4/3 times pi, and then we've got to do times, we've got 1 times 10 to the negative 13th. Sorry, there should be a 1 there. It disappeared on me. And that 1 to the 10 to the negative 13th is also cubed. So to do that, I'm going to get a pretty tiny number for my volume. I'm going to get that my volume is 4.19. I'm keeping an extra digit right now, times 10 to the negative 39. Note that I should not have 3 digits when I get to the end of my problem. I should only have 2. But I'm keeping an extra one as I go. You can actually leave all the numbers in your calculator if you want to. That's actually better, but in case so I could write this down, I didn't want to write out 4.1887902. That would be absurd to write on this thing. But keeping the digits, multiple digits past your significant figures in the middle of the problem helps keep you from having rounding errors. At the very end, I should only have 2 significant figures. I want to point out, there's a chance, sometimes depending on how you put stuff, you might not have gotten exactly this. Make sure you're treating pi as a separate number. Like I have 4 divided by 3, and then multiplied it times pi. Sometimes people can end up like dividing by it or something like that. So just make sure that you're actually doing that if you don't get the number that I got. I'm also happy that if you want to email me or message me, I can look at your problem and your exact number and try to help you figure out what step it is you might be getting that's causing you to get an answer that's slightly off. And I'm checking my work real quick. I made some errors in the last video I don't want to do again. Yep. So this is my volume. So now we're not done. We had to put it into density equals mass over volume. So we have M over V. So we have 1.7 times 10 to the negative 24th grams divided by 4.19 times 10 to the negative 39 cubic centimeters. So we'll plug these in. Divided by. So I got that my answer was 4.1, because now I'm rounding to 2 sig figs, times 10 to the 14th grams per cubic centimeter. So you may not have a good feeling for density yet, but as you learn them, you'll know this number is much, much higher than any density you're usually going to calculate for something. This is because, as we'll learn about in the next chapter, atoms are mostly empty space, but this proton thing in the middle is where almost all the mass is. So if you got rid of all the empty space and just kept the parts with most of the mass, they would be super duper dense. So this is just approximate. Also, there are some assumptions made in this. You could argue the proton's not an exact sphere. Trying to determine the radius of a proton can be something that people could debate about, like what counts as the radius. We're not going to worry about that for right now, just to show you that, yes, protons have lots and lots of mass compared to the rest of our atoms, which is a concept we will get into much more detail in the next chapter. So this one I don't have problems to do. I'm just going to introduce some concepts. We'll do a lot more of energy in later chapters, but I just want to mention it a bit here because it will come up. So energy, we're going to say, is the capacity to do work, and work is going to be defined as an action of a force through a distance. So if we don't cause that force to go somewhere, we're not going to have it say it does anything. It's not going to count as work then. So the SI unit for energy is going to be the joule. And you've also likely heard of an English unit for energy called the calorie. Note that the calorie with a capital C you see on your food label is specifically capitalized because it represents a food calorie, which is equivalent of a kilocalorie. So kcal, since you put a K in front of it, that means that 1,000 of our little calories is equal to 1 capital C calorie. In this class, we're going to stick to using lowercase calories and kilocalories to reduce the chance of confusion. I'm not going to have some trick problem on your test where it has a capital C and you have to know, oh, that's actually 1,000 little calories. No. But it's good to know for when we start talking about calories in class. If you ever thought of the numbers and go, that doesn't sound at all like what I think of on my food label, this is why. We're going to expand on this concept of energy a few times later in the semester. That's why it's very initial here. If you don't yet have a good feel for it, that's okay. We will build on it at least 2 more times. And we'll talk more when we get to particular examples of energy, because it's easier to try to explain once we actually get there. So that's it for this chapter. Good job on making it through the first chapter of my course.